Okay, now an important fact. If I take the intersection of subgroups, I always end up with a subgroup again. This is what can be seen here. If two lines meet downwards, then automatically here this dot corresponds to a subgroup. This is actually trivial, but nothing is trivial until you see it, so let's prove it. So first of all, both subgroups must contain the identity. So the identity also lies in the intersection, so the intersection of two subgroups is never the empty set. This is what we first need to apply the subgroup criterion. Okay, now this is why it is trivial to prove that this is a subgroup. Simply by definition of intersection. If two elements lie in the intersection, then this means that these elements lie in H and at the same time in K. Now, because these are subgroups, by the subgroup criterion, the condensed one from this problem set, this here, AB inverse lies in H and AB inverse lies in K, and this means simply that AB inverse lies in the intersection because it lies in both. And again, by the subgroup criterion, the condensed one, this shows that the intersection is a subgroup. And actually not only the intersection of two groups, but even if I intersect as many subgroups as I want to, I always end up with a subgroup, and the proof is always trivial because of the definition of intersection. All right, now B is much harder. First of all, is it true that the union of subgroups is again a subgroup? The answer is no. So since we already have this nice diagram here, we use it, of course. So let's take as H this subgroup of order 2 and as K this subgroup of order 2. If I take the union of those, and remember both contain simply this element and the identity. There are only two elements, so I end up with this subset here, and this clearly is not a subgroup because, for example, if I compose r squared s with s, I end up with r squared s squared, but s squared is the identity because s is a reflection. And r squared is obviously not in this set here. Well, it's not completely obvious, but you have to convince yourself that r squared, the rotation by 180 degrees, is not one of those reflections here. So this shows in general the union of subgroups isn't a subgroup again. This is why I said here, when two lines meet upwards, you have to take the smallest subgroup that contains both, which means contains the union. And this is in general a larger group than the union. So when is this true, that this is actually a subgroup? Of course, trivially, if one group is contained in the other, then the union is simply the larger of those two subgroups, which of course is a group, subgroup. The hard part to show is that this is actually the only possible case. So only if one of the groups lies inside of the other, the union is a subgroup. And this is what we are going to prove. All right, so if we have two subgroups of a group, and without any hint, I think this is pretty hard. So that's why this exercise, or this part of this exercise, has two skulls. So we have the following: the union of those is a subgroup if and only if one is already contained in the other. They might, of course, be the same group. So H equals K, of course, then the union simply is H, respectively K. Okay, and as I mentioned before, this direction is trivial because if, for example, H is a part or subset of K, then this union simply is K, and K was assumed to be a subgroup. And of course the same for the other case. All right, we prove this by way of contradiction. So we assume that this is true, but that this here is false. Okay? And in the end we will arrive at a contradiction showing that this can't be false, it must be true. This is always the logic in a proof by way of contradiction. So we assume that the union is indeed a subgroup, but that this statement here, which I call green star, is false. Now, the negation of or is and, so we negate those two, meaning H is not a complete subset of K, and K is not a complete subset of H. So then this picture here helps, this Venn diagram. If this is both the case, then it must look like that. So there exists an element that lies in H but not in K. So we choose an element in H without K, and also there exists an element, a small k, in K without H. Now obviously both lie in the union because H is in H, which is a subset of this union, and K lies in K, which is a subset of this union here. But then because we assumed that the union is a subgroup, here this product must lie in the union. So what does it mean to lie in a union? The union is all of this here. It means that it lies in H or in K, or in both. That's not forbidden. That's not an either or, but it must lie in H or in K. Otherwise it can't lie in the union. Now it doesn't make any difference if it lies in H or in K, so without loss of generality we assume that it lies in H. Now we come to the following contradiction. We write K as E times K. E is H inverse HK. By associativity I can move the parentheses and now I have written K as H inverse, which lies in H because H is a subgroup and small h lies in H. And by here we just assume that the product HK lies also in H. And again, because H is a subgroup, then this product here lies in H. But it does not, because we chose K to not lie in H. So this is our contradiction. And of course, if this product lies in K, we do the same with H, write it like that and arrive at the conclusion that H is an element of K, which it is not. So the assumption that this here is false leads to a contradiction, so it must have been true, and we have proven the hard implication. And this really deserves this end of proof box here, because this, without a hint, if you're not really brilliant at math, is, I think, very hard to come up with. But from time to time, I like to pose exercises without hints that are really difficult. So if you're a beginner but are really good at math, then of course you won't be watching my videos, but still you have the chance to think about stuff like that. And if you achieve that, if you did this proof without looking it up, please drop a comment below and congratulations. I could have never done that myself. Even nowadays, I know this trick, but I always have to think hard to write it down correctly or even have to look it up again, because this is really not so easy. All right, last exercise on this also pretty damn long problem set. Gotta start making shorter problem sets. This becomes way too much work. All right, we are classifying the subgroups of the integers with addition, which is clearly an infinite group. The claim is the following: H is a subgroup of the integers if and only if there is a natural number or zero such that H can be written as n times z, which are simply all the multiples of n. I take all the integer multiples of n So this is this set here. Okay, let's prove the easy implication first. If I find a natural number or zero such that H can be written like that, then it is a subgroup. Of course, H is not the empty set. Even if this is 0, I have H consisting of 0. Okay, I want to use the subgroup criterion. If these here are two elements of the subset I consider, then I must show that A dot B inverse also lies in the subset under consideration. Now we have an additive group, so the inverse is not written as to the power of -1, but the inverse of n times L is simply minus n times L, and our group operation is addition. So this is nothing but AB inverse, but in additive notation. And then of course this here is n times k minus L. K minus L is an integer, so this again lies in NZ, so we are done. Yeah, this is actually a subgroup. Okay, now the other implication is much harder. Why? Because we have to find an n, we have to come up with an n. And this is always more difficult than simply checking some criterion. So the easy case is if H simply consists of the number 0, I can of course take n equals 0. So if H is not 0, then I can take the set H without a 0. This contains certain integers. Now I take the absolute values of these, so I get positive numbers. And then I have a collection of natural numbers. And every collection of natural number has a smallest element. We simply accept this here without proof, so I can define n as the minimal element of this set here. This will give me a natural number. And now the claim is this is already the n I'm looking for, namely that H is equal to nz. Now to show equality of two sets, it is often useful to prove that the left side is contained in the right side and the right side is contained in the left side. So we do the easy implication or the easy direction first. So first of all, n is an element of this set, or if not, because I have taken the absolute value, minus n is, but since this is a subgroup, this is what we assumed, I know that plus n or minus n both lie inside of H. And again, we do not write n inverse, but we write minus n instead. So this simply uses closeness under inverses, so plus minus n lie both in H, but then what is n times k? If k is positive, this is simply n plus n plus n plus n, which is an element of H, or if k is negative, this is simply minus n plus minus n plus minus n, which again is an element of H because H is assumed to be a subgroup. So this shows that n times z, which consists of these elements, is a subset of H, because each of these lies in H. Okay, this is also not quite trivial. You have to be aware of some of the subtler points here. But harder is the other inclusion. We have to show that H is a subset of this here. So let H be any element of capital H. We have to show that it is of the form n times k. But now we are in the integers, so I can divide H by n. This means I will find two integers, q and r, such that H can be written as q times n plus r. I could do this, of course, in many different ways, but I can repeat this process until the absolute value of r is smaller than the absolute value of n. All right? This is just division with remainder, and this remainder satisfies this condition here. But now this remainder can be written as h minus q times n. H lies in H, of course. N lies in H. so minus q times n must also lie in H by this argument here. So R is an element of H, but now we have chosen n to be the minimal element of all those. So the only without 0, so the only possible choice for R is actually to be 0, because otherwise the absolute value of R would be smaller than the absolute value of n, which is not possible. All right? So I'm running low on battery, I have to be quick. So by minimality of n, which is the same as absolute value of n, because n is positive, R must be 0, otherwise it would have a contradiction. So H can be written as q times n plus 0 or n times q, which is clearly an element of this set, thus finishing the proof. All right, this was pretty damn hard.